Now we're going to look at compositions and partitions, which are interesting combinatorial objects that are well studied and well explained by the symbolic method. So composition is a simple idea. You want to know the number of different ways to express n as a sum of positive integers. So 2 could either be 1 plus 1 or 2. 3 could be 1 plus 1 plus 1, or 1 plus 2, or 2 plus 1, or just 3. And so forth. There's 8 ways to express 4 as a sum of positive integers, and 16 ways to express 5 as a sum of positive integers. And again, it's easy to guess the pattern. There's 2 to the n minus 1 ways to express n as a sum of positive integers. And that's easy to see with the symbolic method. We start out by just considering integers as a combinatorial class. So let I be the class of all positive integers. So it's just like unary. So we take an atom and we give it size 1, so its generating function is z. If we have 7 of them, then we have z to the 7th. So the generating function for the class of integers is for every integer z to the size of that integer, or if we collect them by n, I sub n z to the n. And what is a positive integer? It's a sequence of at least one atom. And so from the symbolic method, the generating function is z over 1 minus z, so that means that there's one integer for all positive n. And so that seems like a trivial derivation, but again, making these kinds of arguments for things that we understand so well lead us immediately to be able to address more complicated problems with the same basic structure. So now if we look at compositions, what we can do is essentially think of a number as being divided up into smaller pieces just by putting, if we have 12 dots, we can put bars in with the 12 dots, and wherever the bars do, we convert back to unary. So this is one composition, 1 plus 3 plus 1 plus 5 plus 2 equals 12. And if you look at it that way, and again, the generating function in the standard way, then a composition is just a sequence of positive integers. So a sequence of positive integers is a composition, and then grouping by n, we just need to find coefficient of z to the n. But sequence of positive integers, the generating function is immediately 1 over 1 minus the generating function for integers, and that one's z over 1 minus z, and if you do the math, you get 1 minus z over 1 minus 2z for the OGF for compositions. And then expanding that, it's 2 to the n minus 2 to the n minus 1, or 2 to the n minus 1 different compositions. So very straightforward to analyze this combinatorial structure with the symbolic method. You can argue combinatorially if you want. There's n minus 1 spaces between the n dots, and every one of them could have a bar or not, so that's why there's 2 to the n minus 1 possibilities in terms of number of compositions. Now what about partitions? What if we don't care about the order? Same way as we did for trees. So there's 3 partitions of n integers. So we'll take the one that goes in decreasing order. All of these, 1 plus 1 plus 1 plus 2, 1 plus 2 plus 1, and so forth, they all represent the same partition. We'll keep the one whose parts are not increasing. So anyway, just crossing out the ones that appear more than once, there's 7 partitions of 5 elements. Express n as a sum of unordered positive integers. It's not so obvious what the answer to this one is. I think you'll look at the, you're not going to find the 2 to the n minus 1 pattern here. And people have studied this actually quite a bit. There's a thing known as a Ferrar's diagram, which is a 2D representation of the partition, where you just put the parts in order, you just turn them on end and make columns out of them. So if you have that partition, 8 plus 8, and so forth, so that's parts are in decreasing order, If you just turn the dots on end, you get this Ferrar's diagram of the 42 dots, and it's non-increasing, so it's a staircase down. The question is, how many different diagrams are there? So the question is, how many Ferrar's diagrams are there with n dots? And again, this seems like a toy combinatorial question, but actually it's going to require the symbolic method and also saddle point asymptotics. It's one of the most difficult asymptotic problems we'll run into. And even so, not only that, there's lots of applications where people want to study these things, not just analysis of algorithm, but particle physics, and it's related to Lie algebras and representation theory. So you can find these objects studied in physics journals, not just math and computer science journals. So we can do the symbolic method part right here. So if we're going to study the class of all partitions, then the examples that we just showed, it's simply the case that a partition is a multiset of positive integers. So that means that since there's only one integer of each kind, just directly from the transfer theorem that the symbolic method gives us, we have that expression for the generating function for the number of partitions. And to find z to the n of that, again, is quite a challenge. It goes back to Hardy and Ramanujan, and it's asymptotic to e to the pi squared root of 2n over 3 over 4n over square root of 3. And we'll later on touch on that. But from the present context, we get right to the problem with this symbolic method. And this is representative of a huge number of problems where, again, with trees, we express different problems on trees by having different kinds of restrictions on the subtrees. And for these types of problems, you can consider, say, compositions into m parts, or restricted compositions where you don't allow all the integers, just some subset of the integers. Same with partitions. You can do partitions into distinct parts, or restricted partitions where you can take, again, any subset of the integers, and all different kinds of problems ensue from considering these things. Write down the OGF for compositions into parts where the integers are all less than or equal to r. And we'll look at a couple of other ones. How many partitions are there into parts that are powers of 2? Well, that answer is easy, 1, and we'll see why in just a second. Just from the symbolic method, it's 1 plus z times 1 plus z squared, 1 plus z to the 4th, and so forth. So we're looking for the coefficient of z to the n in that. Well, if you just multiply the first two terms, that's 1 plus z squared plus z cubed. And then if you multiply that term by the z to the 4th, you can see the first 4 terms come, and then z to the 4th times each one of them carries the series through to 7. And then same for 8, so you can see eventually you just get sum of 1 plus z and so forth, which is 1 over 1 minus z. So it's just a number of ways to represent an integer as a sum of powers of 2. There's only one. That's sometimes called the computer scientist theorem. Problems of this type are very well studied. One of the most famous ones is due to Polya. It's how many ways are there to change $1? So let's say all you have is quarters. How many ways are there to change a dollar? Well, so $1 is 100 cents, and the number of ways to represent an integer with quarters as a sum of 25s is 1 over 1 minus z to the 25th. So coefficient of z to the 100 in that is just 1. There's only one z to the 100th term. So the only way to change $1 with quarters is 1 with 4 quarters. So that's fine. So what if you have dimes too? Well, it turns out there's three ways to change $1 with quarters and dimes. So you can do that by trying to figure out the possibilities, or we can do it with generating functions too. So number of ways to change $1 with quarters and dimes is coefficient z to the 100 and 1 over 1 minus z to the 25th, 1 over 1 minus z to the 10th. That's the number of ways to represent an integer as a sum of 25s and 10s. So if you multiply out those power series, and look for coefficients of z to the 100, well, you're going to see there's going to be the 1 times a z to the 100th out here. There'll be 2 z to the 50ths multiplied together, and then there'll be a z to the 100th in this one times that one, so there's 3 different things. In fact, what you can do is just throw out the irrelevant terms if you're just looking for the coefficient of z to the 100, and then you get the 3 different ways. That's how many different ways to change a dollar with quarters and dimes, either 4 quarters, 2 quarters and 5 dimes, or 10 dimes. So now what if we, so that's quarters, quarters and dimes. What about if we add nickels? Well, now if we add nickels, you're going to say, well, I want a computer to do the symbolic analysis. Or what about pennies? So how many different ways are there to change a dollar with quarters, dimes, nickels, and pennies? So Polya had a key insight and wrote a paper on this that shows that it's not difficult to calculate this for small values by hand. And it's worth looking at because it illustrates a general phenomenon that very often one thing that we can do with generating functions is use them to get recurrences, and then we can compute with the recurrences to at least know numerical values of the things that we're studying. So what Polya pointed out was that if you have a generating function b of z that's equal to another generating function a of z times 1 over 1 minus z to the n, then you multiply both sides by 1 minus z to the n, and you get this following recurrence, that b sub n equals b sub n minus m plus a sub n. So that gives a way to go ahead and compute the small values. So, so for this example, we're going to add the nickels and then the dimes and then the quarters. Actually, you could do this in other orders too. So add, and we're only doing, since everything's a multiple of 5, we'll only look at the coefficients of z to the power that's a multiple. So if we want to compute b sub n, so we're going to compute b sub 5, then we take a sub 5 and add b sub 0 to it. If we want to compute b sub 10, then we take a sub 10 and add b sub 5 to it, and so forth. So for this line, it's easy to figure out what happens. We just get n plus 1. So now it starts to get more interesting for the next line. So now if we want to know, we start out with the first two are 1, but now if we want to know b sub 15, then we go 10 back, so that's a sub 15, that is the line below, plus b sub 5, so that gives 4. And then 2 plus 4 is 6, 4 plus 5 is 9, 6 plus 6 is 12, 9 plus 7 is 16, and so forth. So add each one to the one 2 back. So to get this one, we get 15 plus 49 is 64, and so forth. And we can just fill in that whole line in that way. And then finally the last line, to get 25, we just go back to 0 and add a sub 25, and then now we can skip 5 at a time because our goal is just to get to 100. So 49, 72 is 121, and then we have 242 different ways to change a dollar. So it's an easy way to do a computation based on the generating function, even though computing this in general might be a bit of a challenge for various different types of restrictions. And if you want to do an exercise, start with this table and say the government switches to 20-cent pieces instead of dimes for some reason. How many ways are there to change a dollar? And you can run through this computation in the same way. It turns out there's a lot fewer. So that's Polya's change a dollar problem. That is an interesting problem related to compositions and partitions, showing how we can use OGFs to address some of these problems.